All right, day 3. Hello, everybody. Welcome back to this series we have here on LinkedIn and also posted now on YouTube. Bam, bam, bam. Yeah, so we have this also posted on YouTube now because some of you asked for it. So maybe I'll include the link in the description as well. So first of all, thank you for all the support. You've been fantastic in terms of sending me like messages in the direct messages feature, being like, "Oh my God, I love this concept and stuff," which really caught me off guard, to be honest. And I really appreciate you reaching out. And it's really motivated me to keep on going. So that now that's out of the way. I would like to proceed with day 3, and as discussed in day 2, we're going to be talking about the transformer architecture and what distinguishes it, and we're specifically going to be looking at the attention mechanism in these networks. So as we discussed in the previous 2 episodes, the transformer architecture has become the backbone essentially of modern AI. And we'll look at the encoder decoder that's in the heart of this architecture and the role of multi-head self-attention in this whole mechanism. We'll also look at the feed-forward network that's there, and how the interaction between all of these creates the encoder-decoder architecture as we know it. So the transformer, the original transformer, and we're not going to talk about the modifications today. When I refer to transformer, I'm referring to the transformer that was introduced in 2017 in the paper "Attention is All You Need" by Vaswani and others. And in that paper, the transformer is divided into 2 parts: the encoder and the decoder. So when you're thinking about an encoder, you can think about a component that processes the input that's given to it. So it's essentially a sequence consumer. So you can think about it like that. And it takes that and it turns it into a rich contextual representation of that sequence, which conveys the meaning. And it's in a format that the computer can actually start the process and the model can essentially manipulate inside it. On the other hand, we also have the decoder, which consumes that rich representation essentially and tries to generate an output sequence. So that's done in an autoregressive manner, or let's call it step by step. So internally, each decoder is built up of 2 sublayers, let's call it like that. So there's the self-attention block, and there's also a feed-forward block. So self-attention we'll get to, but the feed-forward block is essentially a set of fully connected nodes. And if you're familiar with neural network method terminology, that's essentially a fully connected layer, a series of fully connected layers, actually. And in terms of the decoder, generally speaking, we have 3 layers. And that's the self-attention over the generated tokens thus far. We have the cross-attention and to the decoder output, and we also have the feed-forward network, similar to the encoder. And then by stacking many of these layers together, we allowed the model to actually start to capture the very complex dependencies and the long-range dependencies that exist between the input constituent factors, so essentially the tokens. So we talked about like the overall structure, and it was pretty technical, so I just want to explain self-attention a bit more clearly, what it is, in a more understandable manner. And to understand this attention, the idea of self-attention, I would actually highly recommend 2 things. One, the post, the first blog post that I've included in the description, and also the video I've included. For me personally, the video was amazing. I love the video by 3 blue, 1 brown. Great channel overall. So let's go into self-attention. The real innovation, to be honest with you about self-attention, is that every token contributes to the entire meaning. So every token is essentially turned into 3 vectors, which are called the query vector, the key vector, and the value vector. And the model computes attention scores by comparing queries against keys. So how you can think about this is that each token represents a specific value, and it also asks for specific values. And by querying over a sequence, it tries to capture the meaning of the entire sequence altogether. So the way that it works is that the model computes the attention scores by comparing queries against keys, and the model essentially tells us how relevant other tokens are. And then these scores are the weights that are given to the values, so the value vector. So each word representation becomes a essentially context-aware blend of the entire sequence. So if you have Roham is currently recording a video, so the video also conveys the meaning of Roham, and also conveys the meaning of currently. So it's a rich representation of the word. So essentially, instead of looking only at the immediate past as like it was common previously with like more traditional sequence models, the model can connect any 2 words directly. So it doesn't matter whether they're next to each other or hundreds or even thousands of tokens apart. And this essentially makes the transformer architecture vastly better than the recurrent models that we talked about, or the more traditional sequence models. And having this idea of attention, and it's called self-attention here and there. So when you have self-attention, you can stack it up across different heads of each transformer layer, and then you get something called multi-head attention. So the model learns several separate sets of query key and value projections in parallel, and each of these focus on different patterns. So if you're thinking about AI for SE, for example, you would be thinking of the different heads capturing different aspects of syntax, semantic meaning, how different concepts are approached in different programming languages, for example, how the relationships are between variables and, I don't know, like their classes, for example, something like that, like it's different aspects are captured by different heads, and these contribute different perspectives to the entire meaning. So the model is not like a very monotone model, but it's like an actual mix of different views of the same topic. And that just increases the capabilities of the models. And until now, we've talked about a sequence being encoded into like a representation, but there is something that we miss, and that's the notion of sequentiality in your data. Because, for example, when you're writing code, it matters whether you first write the identifier or for example, write the equal sign, or whether you write the identifier first or the type annotation first. So we have to encode somehow that that notion of sequentiality in your encoding, and that's where the idea of positional embeddings or positional encodings come into play. And using some mathematics that I don't really want to go into, it technically tries to incorporate that aspect of sequentiality into the encodings. So it injects, let's call it like that, it injects information about the sequence order into each token embedding. So the model can actually use that information as well. And essentially after each attention, each position goes through a small feed-forward neural network, and I explained what that was. This gives the model non-linear capacity, and it also it helps it to transform the representations. And together, these two, so it's like attention and feed-forward networks can be computed in parallel across the sequence. And that's the distinguishing factor with the transformer architecture with the more traditional RNNs and sequence models, where they had to process everything step by step. And this allowed so this architecture and this setup allowed the transformers to be faster and more scalable. So yeah, that was essentially like a quick run through the transformer architecture. So to sum up, the core of the transformer architecture is this idea of self-attention, and when you combine it, you get multi-head attention, which gives you a dynamic view of the context, and the feed-forward transformations give you some other additional capabilities essentially to actually learn, and because of this composition and this structure, you also have that notion of efficient parallelization. And with this architecture, albeit that's a very much so a overgeneralization, so the whole architecture has undergone a lot of change. This architecture and this idea as a whole has become so powerful and essentially the backbone of modern AI. So that was day 3. In day 4, so probably tomorrow, I assume, we're going to focus on how training on large amounts of data can give you better models as a whole, and gives rise to this idea of foundation models. Thank you for sticking around. Thank you for watching until the end of the video. If you like this, please like, share. If you're on LinkedIn, connect. We can get to know each other better. And if you're on YouTube, please consider subscribing. Thank you for your attention, and until, pun intended actually, thank you for your attention, and until the next video. For now, bye.